Now we move to transformation of strain components. A transformation of strain component is one of the fundamental concepts in structure mechanics involving the change of strain components from one coordinate system to another. As we discussed, the strain components describe how an object deforms under the applied forces or loads. First of all, we will discuss the transformation of strain in a 2D space, and then afterwards we will discuss the transformation in the 3D space. The transformation of strain components between the coordinate system will be governed by a linear transformation that is similar to transformation of vectors. So we can see that there is an element having the stress components shown. The element is subjected to general state of plane stress. The reason we are calling it plane stress because we are ignoring the stresses in the third dimension. The normal stresses are assumed to be tensile and they elongate the element in x1 and x2 direction, whereas the shearing stresses distort the element through the shear strain gamma 1 2 as shown in this figure. Our coordinate axis, which is shown in purple, corresponds to the left corner of the element, or in other words, the coordinate axis has got an origin at the left corner of the element. The effect of these strains on any line element OA is shown in this figure. So we have the element which is OA, and that OA changes its angular position by a very small amount that we call beta, and also OA is elongated to OA dash. The movement of A to A dash is the vector sum of the axial elongations and the shear distortions. So horizontally, we say that A has moved by strain 1 into D1, where D1 is the horizontal dimension of this element. So this element is considered horizontally as D1 and vertically as D2. The reason strain 1 is multiplied with D1 is that we are trying to find out our deformation, which is equal to strain by the original length D1. Using the same logic, we can multiply the strain 2, which is in the x2 direction, to the original length D2. And the shear distortion gamma 1 2 can be multiplied with D2 in the x1 direction. So as we can see in this figure, the movement towards the left is gamma 1 2 times D2. In other words, this is just tangent theta is equal to perpendicular by base. Since we are dealing with very small distortion, so tangent theta is approximately taken equal to theta, and theta is gamma 1 2. That gamma 1 2 is multiplied with the base D2 to get the shear distortion, which is gamma 1 2 theta to D2. Please note that this movement of A is highly exaggerated to show how the vector sum may be resolved into two components, that is, one parallel and another one perpendicular to OA. The parallel component A double dash, A dash, represent the increase in length of OA, whereas the perpendicular component A double dash causes the change beta in the angular position of OA. The magnitude of A double dash A dash is found by projecting strain 1 D1, strain 2 D2 and gamma 1 2 D2 upon the direction OA. Thus, we get A double dash A dash is equal to strain 1 D1 cos theta. So, strain 1 D1 component along OA plus strain 2 D2 sine theta, which is this one, strain 2 D2, and its component along OA minus gamma 1 2 D2 cos theta. So gamma 1 2 D2 and its component along OA. Please note that instead of finding the components upon OA, we can also find it upon OA dash because the angle between OA and OA dash is very small. Please also note that along OA dash, strain 1 D1 is in the direction OA dash. Strain 2 D2 is again in the direction OA dash, whereas gamma 1 2 D2 is in the direction A dash O. That's why negative appears in the case of gamma 1 2 D2 cos theta. If we assume that OA is equal to ds, or in other words, the length of OA is equal to ds, divide A double dash A dash by ds, we will get the extension of OA, which is equal to strain 1 d1 cos theta by ds, strain 2 d2 sine theta by ds minus gamma 1 2 d2 cos theta by ds. Since d1 by ds is cos theta, d2 by ds is sine theta, and d2 by ds again is sine theta. Plugging the values, we get the extension of strain A in terms of strain 1, strain 2, and gamma 1 2. The angular deviation beta can be found in a similar way. We have to divide A double dash by the length ds in order to determine our angular deviation. Projecting the movement of point A on the direction perpendicular to OA, we obtain AA double dash as strain 1 D1 sine theta minus strain 2 D2 cos theta minus gamma 1 2 D2 sine theta. Once this is found, again we can divide this whole expression by ds and plug the values of d1 by ds, d2 by ds. We get beta equal to strain 1 cos theta sine theta minus strain 2 sine theta cos theta minus gamma 1 2 sine square theta. As we know that the total change in the right angle between OA and its normal OB defines the shear strain for an element that is located theta from the x1, x2 axis. That is why we have to work out our angular deviation OB, which is at theta plus 90 degree. So plugging theta plus 90 degree in the beta equation, we get beta dash as minus sigma 1 sine theta cos theta minus strain 1 sine theta cos theta plus strain 2 sine theta cos theta minus gamma 1 2 cos square theta. Please note that beta and beta dash rotate in the opposite directions. So their absolute sum is equal to their algebraic difference. That's why the absolute sum is taken as beta minus beta dash. So, and that gives us strain 1 2 sine theta cos theta minus strain 2 2 sine theta cos theta plus gamma 1 2 cos square theta minus sine square theta. Thus, we have derived the axial strain and the shear strain for the 2D element.